Welcome to this next lecture. After exploring in the previous sessions how data flows through energy systems and why it is crucial for decision making, we now turn to a different but closely related topic: how machine learning models are actually built and developed. Machine learning has become an essential tool in modern energy systems, whether for forecasting, anomaly detection, optimization, or automated control. But behind every model, no matter how sophisticated it looks from the outside, stands a structured process, a workflow. This lecture has one main learning objective: describe the key stages of a machine learning workflow. As simple as that may sound, each of these stages contains a number of steps, decisions, and iterations that shape the outcome of a model. In the next slides, we will go through each one and highlight the typical challenges and best practices. So here we see an entire workflow at a glance, from raw data to deployment. The slide shows 5 major blocks. First, data preprocessing. This includes data collection, data cleaning, and then the data transformation. Second, the feature preparation step. Here, we engineer, select, or even extract the features that will feed into the model. The next is the model development. Here, the engineer chooses a model type, trains the model, validates it, and tunes its hyperparameters. The next step is the validation and refinement step. This is where the model is tested and improved based on performance. And then the model deployment. In real-world applications, the model runs continuously and may need monitoring and updates. Importantly, the workflow distinguishes between offline development and the online learning or deployment. This distinction matters. Offline training allows extensive experimentation, while the online deployment requires the reliability and often operates under real-time constraints. To make this process more concrete, the example shown here illustrates how the workflow behaves in practice. We begin with data processing and feature preparation, perform the training, and then check the accuracy for the resulting model. If the accuracy is not sufficient, we loop back. Perhaps we clean the data differently, or we try new features, or select another model. This iterative path continues until the required accuracy or performance criterion is met. Once the accuracy is acceptable, we move to prediction. And after deployment, the system includes the monitoring and the alerting, which ensures that the model remains reliable over time. This cyclical, iterative nature is typical. Machine learning is rarely a straight line from start to finish. The first major step is data preprocessing, which is shown visually here, using icons representing the data cleaning, pipelines, the transformation processes. So this stage usually contains 3 tasks. The data collection. Here we gather relevant data from sensors, logs, databases, or historical archives. Then the data cleaning. We remove errors, handle missing values, and ensure that the data is consistent. Then the data transformation. Here we normalize, scale, or encode the data so that it is usable for machine learning algorithms. You can see at the bottom illustration the funnel concept, that raw data enters messy and inconsistent and leaves the process in a clean, structured form ready for modeling. Once pre-processing is done, we enter the stage of feature preparation, which plays a crucial role in the final performance of the model. This step can include the feature engineering. Here we create new informative variables from existing data. Then the feature selection. Here we identify the most relevant features and remove redundant or noisy ones. Then the feature extraction. So here we transform high-dimensional data into more compact representations. For example, using principal component analysis or other dimensionality reduction techniques. The diagrams on the slide show how data, can transform and how visual in separation between classes can be revealed by good feature preparation. Strong features often outweigh sophisticated model choices. Good features make learning easier, faster, and more accurate. Next, we arrive at model deployment, which is where most people imagine machine learning tasks takes place. But in reality, it's only one part of the workflow. This stage contains 4 key activities. The model selection. Here we choose the appropriate type, a linear model, a tree-based method, a neural network, and so on and so forth. Then the training. Here we fit the model to the training data so that it learns the pattern within it. You can see how training and deployment differs when models are updated online or offline. In online settings, new data can trigger model updates continuously, which is common in dynamic environments like in the energy system. For example, when an electric vehicle is charging schedule is updated for a specific car driver. Then the validation. Here we test the model on validation and testing data to assess how well the model generalizes to other conditions which are not part of the training data. Then the hyperparameter optimization. Here we tune parameters that are not learned automatically, such as the depth of a decision tree or the learning rate of a neural network. On this slide, you also see 2 popular methods for hyperparameter optimization, the grid search and the random search. Grid search tries a structured set of possibilities for these parameters, while random search samples randomly within a space, often surprisingly effective. So generally, we recommend random search as it performs better than grid search. Let us summarize what we have covered. Machine learning development follows a structure ranging from data preprocessing to feature preparation, model deployment, and development. Each stage involves specific tasks and decisions that influence the final performance. The workflow is iterative. Accuracy may require multiple cycles of refinement. And once deployed, a model becomes part of a living system, requiring monitoring, updates, and continuous learning. With this understanding, we can now move on to applying these workflow concepts in the context of energy system and their data-driven applications.